Section 10.2 is vectors. Most of us should be familiar with vectors at this point from other courses, but nonetheless we'll do a brief intro on them and some applications. We'll mostly be adding vectors, subtracting vectors, and calculating scalar multiples of vectors, calculating their magnitude, forming vectors between 2 points, talking about standard basis vectors, and ultimately just a small physics force problem involving vectors as well. So recall that a vector is the representation of a quantity with both magnitude and direction. So it has a length and it's pointing in some specific direction. The tail end of a vector, or the initial point, is the dot, and the terminal point is the end of the arrow. So initial and terminal points covered. Two vectors are equivalent if they have the same magnitude and direction. If we're going to add two vectors u and v, we take the initial side of u, place it at the terminal side of v, and we go tip to tail in vector addition. That's geometric vector addition. So let's look below. We're asked to draw two arbitrary vectors a and b. We've already taken care of that. It just means any two vectors, however we like. Then they ask us to draw their sum, a plus b, using the triangle law. So that is essentially the following. I'm going to pick up b, I'm going to match its tip, the tail of it to the tip of vector a, and we'll walk the path to see what new vector arises. And we go from our initial point here to here, and where we arrive at is a vector which is this one right here. This is our vector a plus b in black. So the result of traveling the path of vectors going tip to tail is the sum of those two vectors. Okay, let's see something similar. Scalar multiples of vectors. So scalar c, in other words a real number, something without direction, is just essentially going to rescale the magnitude of a vector v. Right, so we'll multiply some number by a vector that's either going to shrink the vector's length or extend it. The only way it could change the direction is if c is less than 0. It'll point the vector in the opposite direction. Okay, the difference of two vectors is just u plus negative v. So essentially we point v in the opposite direction and then we add it to u in the tip to tail fashion that we just saw. So let's do a combination of these two things, scalar multiplication and vector differences. So we're asked to calculate a minus 3b. So perhaps the first thing to do, given these two vectors a and b, is we need to look at b and calculate 3b, and then we'll find negative 3b from there. So maybe an easy way to do that with cut and paste method is to copy this vector, tip to tail for, that's 2b, and this tip to tail gives us 3b. Okay, so overall the vector we've now created is 3b. Okay, now one last thing is that this vector is actually pointing in the opposite direction because we want to calculate negative 3b. So there is, that's roughly correct, negative 3b, to label that, negative 3b. And instead of pointing in that down and right fashion, it's pointing upward. So we've now formed negative 3b. In order to find the vector a minus 3b, all we need to do is take negative 3b and put it tip to tail to the vector a. So here's our vector a. We'll label it below, vector a, and we'll take a copy of negative 3b, and we will paste it tip to tail to a, and the resulting vector here looks like this vector here in red. Vector here in red, and that is the vector a minus 3b, the resulting vector from the tip to tail addition. So vector differences are essentially vector addition, just with vectors reflected in opposite directions. Scalar multiples are just either pointing the vector in an opposite direction or just changing the length of that vector. So pretty simple geometric concepts. Now, vector coordinate systems. So we'll often refer to vectors in terms of their components, and an xy components for R2, xyz components for R3, either the two spaces that we might work in this semester. So we'll commonly see these. Now, vector notation will be angular brackets. Angle bracket U1, U2, U3. This would be a vector in R3 since it has 3 components. If we're given 2 points, note that notation for points is different than the notation for vectors. One being that these angle brackets are present versus the parentheses in these. So points have parentheses, vectors have angle brackets. The other thing you might notice too is that vectors are usually denoted in bold print. If we're not typing these things, then we'll put an arrow over the top to symbolize a vector as well. Okay, in order to calculate the vector between the points A and B, we have here A and B. We need a formula for that. That's pretty simple. We take all the components, each component of B minus each component of A, or vice versa, is just fine. It just depends on what they're asking for. The vector from A to B is the one that we're given here. This is A to B. Okay, if it was B to A, we would swap each of these differences for x1 minus x2, y1 minus y1, etc. Now, let's look at the example below. It's already worked out, but we can walk through the steps of it. We're asked to determine the vector from the point 0, -1, 5 to the point 4, 2, 10. So it's 2, 4, 2, 10, so we'll subtract from these components. So it's 4 minus 0, first component minus first component, 2 minus -1, 10 minus 5, our resulting vector is below. So pretty straightforward. That is adding and that is forming a vector between 2 points, from one point to another. Remember that 2, the other one, is the first set of coordinates in the differences. Forming a vector. Next up, magnitude of a vector. We're familiar with this from R2. Recall that the magnitude of a two-dimensional vector is the square root of each of its components squared and added together. Well, for R3, we just extend this with a third component. We square the third component, put it in the sum, take the square root of everything. So find the magnitude of A equals 1, -3, 4. We see that that's a vector given the angular brackets and the fact that A is bold. And they're asking for the magnitude. The magnitude of a scalar is really just the absolute value, so somewhat trivial. So the magnitude of A is first component squared plus second component squared plus third component squared, square root of all of that. Alright, adding these things up, we end up with square root of 26. So our magnitude of this vector is root 26. That's about all there is for finding the magnitude of a vector. Properties of vectors, so a lot of things that we would expect to be the case in terms of adding these things or subtracting them in scalar multiples turns out to be that case. So we can commute vectors, adding them in one order or another doesn't matter. We can associate, so we can add them in different orders if we like, or add 3 in different groupings. The 0 vector added to any vector A is equal to that vector A. And we can go down this list and see more or less what each of these is telling us. This is saying that we can multiply scalars times vectors in any order which we like. This one is also somewhat important. We can distribute a scalar multiple across the sum of two vectors. Now these things seem like they're trivial because they come from the real numbers. They are something that really should be proven, but maybe the textbook's got a nice proof for it. It's a fairly simple, straightforward scenario. But let's just have a look at perhaps using some of these rules. So we're asked to evaluate the vector expression. That's probably just another word for simplify this vector expression. Maybe what we want to look at into a single vector. So we have a scalar times a sum of two vectors, one of which is multiplied by another scalar. So really there are a lot of things we could do to start this. It looks like here I've chosen to distribute the factor of 2 or negative 2 to each vector, right? So then we've broken the parentheses. Negative 2 is times each vector. That's from rule E, to distribute a scalar product, a scalar multiple across the sum of two vectors. Now that gives us a positive 6. Negative 2 times this vector is the result of that. And we add these vectors up and we end up with 6, negative 8, negative 38. Again, when you add vectors, you're just going to add them component-wise. 6 plus 0, 6. 0 plus negative 8, negative 8. Negative 30 minus 8, negative 38. So there's our simplification for that vector, writing it as a single vector now. Okay. Next, getting a little bit more interesting, the standard basis vectors. Again, if you've been in a physics class at this point, you've probably seen these standard basis vectors. For R3, we have I, J, and K. So just sort of conventional names that we've given them. When we write these, instead of printing them, we'll have hats on them. We'll call it I hat. It's essentially the same thing as the bold J. It's just conventional to do that as well. So if we're asked to write a vector given in bracket notation as a linear combination of the standard basis vectors, what they really mean is just rewrite your vectors so that it's a number times each one of these, which when added together gives you back your original vector. So let's see how that goes. I've taken 7, negative 2, 11 right here, and we'll split it up. This is equal to the vector 7, 0, 0 plus 0, negative 2, 0 plus 0, 0, 11. Sure, if we add those three vectors together, we obtain what we started with. So we're decomposing it so that each of these places looks almost like our standard basis vector. But if we look at 7, 0, 0, I'll rewrite that one, and I think we'll see the rest from here. 7, 0, 0. Well, that's equal to 7 times 1, 0, 0. Well, that is the vector I hat. Okay, so that's how we're able to decompose this so quickly. Really, you don't even need this step in the future, this one right here, because you can just look at this vector and say this will be 7i minus 2j plus 11k. Hats for all those letters. Okay, so vice versa, write the vector given by 9i minus 2j minus 4k in vector notation. Well, there it is, 9, negative 2, negative 4. It's really that straightforward for these standard basis vectors. Okay, a unit vector. A unit vector is a vector whose length is 1. So if we take a vector u and we divided it by its magnitude, given here, and then we take the magnitude of the result, right? Let's see what happens in this situation. So if we just were to take this vector u, divide it by its magnitude, we'll end up with a new vector because we're dividing by its magnitude. Once we take this magnitude, we turn that vector back into a scalar. So the result of this should be something that looks like simply a scalar. And we're just trying to prove that if we do that, then the resulting vector has magnitude 1. Well, since this is a scalar, it can be factored out of this magnitude operation. So we have 1 over the magnitude of u, but the result, what's left in this magnitude operation, is the magnitude of u. So the magnitude of u divided by the magnitude of u is equal to 1. So that's why this works. So if we ever need to find a unit vector in the direction u of a given vector u, then all we need to do is divide by its magnitude. Okay, so we'll use that formula to come up with our unit vector. In this case, we're given 9i plus 4j minus root 3k hat. Okay, so all in one shot, I'll write it down here. This is 1 over the magnitude of u, and we see 9 squared plus 4 squared minus plus negative root 3 squared as the magnitude formula suggests. This is our vector u. Alright, we work this out. This comes out to 1 over 10. We can multiply this into each component of the vector through vector or scalar vector multiplication. Reduce this one here to 2/5, and we have our final answer. So that is finding a unit vector in the direction of a given vector. You just divide the vector by its magnitude, You can probably leave it in this form most of the time, but WebAssign, just pay attention. They might want something like this. Okay, so our last example is an application. So vectors are often used in terms of force diagrams. A vector can represent anything from position to momentum to force to velocity, anything with a direction and magnitude or a scale and magnitude. Okay, in this case we're going to be talking about resultant forces, the sum of vectors acting on a single object produces a resultant force. So what we've got in the problem is we have a 150-pound weight. It's supported by two cords which are attached to a horizontal support above the weight. They come together at a common point to suspend the weight, to attach to the weight. One cord makes a 40-degree angle with the horizontal support. The other cord makes a 20-degree angle with the horizontal support. And we're asked to find the tension and forces in each of the cords along with their magnitude. Okay, or the tension slash forces, sort of the same thing. In this case, our forces are tensions on these cables, cords. Now, here's the picture of that. Horizontal support, we've got 40 degrees with one of these cables, 20 degrees is the angle formed by the second cable. We have a 150-pound weight at their common attachment point. This is a downward force, the only vector we can write down right away, of 0, 150. So we place that in where we can. We've dropped this altitude just to make some of the trigonometry make sense. So we look a little closer. Tension 1, or the tension in cord 1, is actually right here. So this is, if we look at our triangle, cosine of 40 degrees, well, this is the adjacent over the hypotenuse. So the magnitude of this tension, T1, is equal to, the horizontal component of this force, T1, is equal to cosine of 40 degrees times the hypotenuse. Okay, so work the trigonometry of that out off to the side. I don't want to clutter this picture up too much more. The reason it's negative is because we're just deciding that this direction is the negative direction. Okay, we could go the opposite way, but one of these is going to have to be negative for T1 or for T2. Okay, now similarly for the vertical component of this force, the y component of the vector, well, that's this side over the hypotenuse is equal to the sine of 40 degrees. That means that hypotenuse times the sine of 40 degrees is this vertical force right here. And that's exactly what's in this box, or this entry in this component. Now, similarly over here, you can check this one. We've got T2. It's decomposed into its tension, whatever the magnitude of that tension is, and its component along the horizontal direction is cosine 20. This one's pointing in the positive direction, so that's good. And sine of 20 degrees. This one's, note that both of these are pointing upward to support that weight, so that's the positive direction we've chosen there as well, somewhat implicitly. So these are the vectors in terms of their tension magnitudes. We'll use these at the very end of the problem when we calculate the actual vectors themselves. For now, I'll just leave them to the side. Now, the physics of the problem gives us these force equations here. So we look at the vertical components, okay, of each of these tensions, and we realize that, okay, in sum, they're supporting 150 pounds, right? Now, T2 is contributing from its vertical component the magnitude T2 times sine 20 degrees. Similarly, the tension from the leg 1, or tension 1. Okay, magnitude times sine of 40 degrees as well. Now, that takes care of the vertical components. That gives us one equation. Note we have two variables in it that we don't know yet. Okay, the horizontal component, on the other hand, well, it's not supporting any weight horizontally. These two tensions are pulling away from each other, but nothing's moving, so they're canceled out to 0. So they should be equal to each other, essentially, is what this is saying. If we add up these two horizontal components, they're summing to 0. Another way of seeing that is just to move this over to the other side so it's positive, and we see that the horizontal component of this tension is equal to the horizontal component of that tension, and that's exactly what we expect for this thing to be stable. With these two equations, recognize that sine of 40 degrees, sine of 20 degrees, cosine 40, cosine 20, these are all constants. We have two unknowns, t1, t2. So this is systems of equations. We use systems of equations and we can solve for magnitude of t1, magnitude of t2. And we have, well, before we plug everything into a calculator, it should look like this, just so students have a hint as to what to fill in here. Similarly, T1, we'll have picked this equation up along the way to solve for it. So once we know T2, we can find T1. Well, once we evaluate this expression to find T2, we end up with 162.76 rounded to 2 decimal places. Similarly for the magnitude of T1, rounded to 2 decimal places. Now we've got those magnitudes of each of the forces. That was one of the questions. So that's an answer. That's good. All set. We're done with that. The last thing we need to do is to form the vectors in this problem that they're asking for. So we go back up here and use this formula and this formula for T1 and T2 respectively. And what the result of that is this. So for T1's case, 132.68 negative that times cosine 40 degrees. Same 132.68 times sine of 40 degrees. And this is how we end up with T1's value. Similarly for T2. Note that the book works out a problem very similar to this, using very similar steps. Maybe there are more details there that could help, but this is the gist of that. I didn't want to drag everybody through every belabored step. There are some details for the reader to fill in, but the bulk of the path is there for students to follow. All right, good luck, get to work.